Hypothesis testing for population proportion. So far, what we have studied in hypothesis testing was to test the hypothesis regarding the average, the mean in the population. But mean is not the only parameter in statistics. We have other parameters such as proportion. Proportion is also an important parameter. So now we want to talk about hypothesis testing regarding proportion. In some situations, you want to test a hypothesis about the proportion of an event of interest in the population. So what is the procedure? The procedure is kind of similar to what we had done before, except that here instead we're going to talk about the proportion and the tested statistics appropriate for proportion. So we begin by selecting a random sample. That's we're going to gather information, gather the evidence, and we're going to compute the sample proportion p hat. So previously we were testing for the average, the mean, so we are computing x bar, the sample average. Here we're going to gather sample and we're going to compute the sample proportion p hat. Then we can use a z-test for the proportion. So the z-value of p hat. So that would be the z-stat, the tested statistic would be a z-stat, and that would be the sample proportion, that's p hat, that we compute from the sample, minus the proportion which comes from h naught. So h naught would say, for example, p is equal to p1, for example. So that comes from here. So always the value of parameters in the tested statistics comes from the null hypothesis. And then we have the standard deviation, which is the square root of p multiplied by 1 minus p over n. Z-stat, the tested statistics, is a random variable that follows a normal distribution, a standard normal distribution with an average of 0 and a standard deviation of 1. Now let's see an example for hypothesis testing about population proportion. Siemens has developed a new process in their new facility in Canada. We want to test whether the new process can increase the percentage of products accurately manufactured, or the good quality product, and therefore decreases the number of defects products, which is the bad quality product. Previous processes have had an 85% rate of accuracy. Data has been collected for this hypothesis testing and experiment from a sample of 100 products produced by the new process. The results indicate that out of these 100 products, 94 of these products were accurately produced, good quality. We want to construct a hypothesis testing and test this hypothesis at 1% significance level. So we want to do a hypothesis to see whether the proportion of good quality product have increased or not. Let's now solve this example. To do that, we need to go through all the steps of hypothesis testing. The first is to formulate the hypothesis. That's writing the alternative hypothesis and also the null hypothesis. To do that, we need to realize we are talking about the proportion. So the parameter that we have to address in a hypothesis would have to be the proportion p. So we need to talk about p both in the null hypothesis and in the alternative hypothesis. So let's figure out what should the hypothesis be. Should it be a two-tailed test, a lower tailed test, an upper tailed test? So let's go back to gather information from the problem statement. It says we want to test whether the new process can increase the percentage of products accurately manufactured or the percentage of good quality product. So this tells us that there has been a change. That's the new facility built, and they are expecting a change in the percentage of good quality product manufactured. So this is obviously against the status quo, against what was known before, against the already existed condition, which is the null hypothesis. So here, this gives us a clue about the alternative hypothesis, about the change. So we're going to use this information to formulate H1, the alternative hypothesis. This says that the percentage of accurately manufactured product, that's P, has increased or can increase from the previously known 85%. So this is how we formulate the alternative hypothesis. It would say P is greater than 85%. That means the percentage of accurately manufactured product or good quality product has increased from the previously known 85%. On the other hand, H naught, which is the null hypothesis, would oppose this alternative hypothesis and would actually state the status quo. And what is that? So we already know how to write that. To oppose this is going to turn from greater than into less than equal to. So it would say P is less than equal to 85%. And that means that the percentage of accurately manufactured product is as the same as before or less than that. It doesn't really matter. In some notation, they actually show this by equality, and some they show it by less than equality. Anyhow, the null hypothesis would state that the proportion has not changed. The proportion of accurately manufactured product, good quality product, has not changed in the new facility. So this is our first step. We formulated the null and alternative hypothesis. Now we need to go to other steps. We need to gather information. That's taking a sample and computing the sample proportion, which we already have it in the problem statement. They have taken a sample of 100 items, and out of those 100, 94 are accurately produced or good quality product. So that means that 94 out of 100, that is P hat. P hat is 94%. So we have the information. The test statistic value has to be computed based on the sample proportion. And the test statistics is a z-test. And the formula is this. That's just the z value of p hat. And that's p hat, which is 94% based on what we had here, minus p. And this p comes from the null hypothesis. That's 85%. Always the value of the parameter in the test statistics comes from the null hypothesis. So we have 85% divided by p, square root of p, multiplied by 1 minus p, divided by n. And we plug in all the numbers and we compute the solution, and the value of test statistics is 2.52. Now we have an upper tail test. So that means that the rejection region is on the upper tail or right tail, and we're going to have only one critical value. This is z of alpha, which is z of whatever level of significance you want to test it. For example, suppose that we want to test this at 5% significance level, then you have to find the critical value for 5%. And then you need to see whether the 2.52, the value of test statistic, would fall in the acceptance regions or rejection region. That means is whether it's greater than the critical value or smaller than that. So the problem says already gives us a clue at what significance level should we test this. It says 1%, so we're going to go with the z of 1% significance level or critical value. Z of 1%, you can find it from the table, and that's actually 2.33. And 2.552, the value of test statistics, is actually greater than 2.33. That means that the value of test statistics would fall in the rejection region. So we end up rejecting the null hypothesis. We're going to reject the null hypothesis in favor of the alternative hypothesis, meaning that the new facility has increased the rate of the accurately manufactured product. Also, if we compute the p-value for this, we can use actually Excel to do that. The p-value computed is equal to 0.0059, which is a very small number. It's almost 6,000, which is less than 1% the significance level. So we're going to reject H0 also based on the small value of p-value.